Hey fellow hobbyists, today we're going to take a look at F-amps and null pixels to see just how far we can take those signals for our light shows with each one. For test signal generation, I'll be using Falcon differential receiver boards and just using the test patterns that are on those. Connect those directly to the F-amp or null pixel, then adding lengths of cable that will increase throughout the test to the oscilloscope and then to 100 LEDs. Now, if you're interested in the details of what these signals look like and kind of what I saw on the oscilloscope and characterizing those and a lot more information that I have in this quick summary coming up, stick around after that summary and I'll show you a lot more details about what I was seeing as I looked at these signals on the oscilloscope. But if you just want a quick summary, I've got a table for that. So this summary of the data shows very clearly that the F-amps outperform the null pixels. I believe that anyone who's worked with these devices understands that's the case. Here's it at 75 feet. You can see from the LED behavior that the F-amps worked great and the null pixels did not. That's pretty obvious when you look at the signal characteristics as to why. When we look at the pulse width for the bits, there's significant margin with the F-amp, whereas there was no time above threshold for the null pixel. In other words, the pixel is seeing no data. Same thing with nominal voltage levels. They were just too low with the null pixel to do anything at 75 feet. In fact, the null pixel really doesn't perform at all until we get down to the 35-foot range, where at least the pixel behavior was good, but right here, this negative 86 nanoseconds for the pulse width above threshold, that means we're in design margin territory. So that means sometimes it'll work, sometimes it won't. I wouldn't recommend running null pixels at distances that put the signal anywhere under design or in the design tolerance. We want to be at least at the nominal values. I hope this table was helpful to you. If you found it useful, please feel free to like and subscribe to the page as I continue to do more of these deep dives into some of the technologies that we love to use in our hobbies. Thanks again, and if you want to see some of the details that went into the analysis, stick around and you'll get to see some of the raw footage as I went through this. Thanks. Now, before we can start looking at test results, I wanted to give a quick overview of the signal that we're looking for so that we can see that comparison. Important note on this WS2811 chipset is that there are two data speeds. The fast speed is what almost all of our pixels that we buy for light shows are going to use. In fact, I've never seen a slow speed pixel, but I'm sure they're out there. That's important because it affects the signal timelines that we care about. So if we go down to this table, it's going to tell us some very important things. It's going to tell us what the voltages and durations are for the signals. So this is going to tell you how it forms a 1 or a 0 bit, though it's for low speed time. So all these times will be divided in half for this node because we're in high speed mode. And then the other important thing we want to know is what are the voltages at each of those values. So let's find that in here. Here we go. And that is told here at the voltage for a high value, the voltage for a low value, and the hysteresis voltage. A value is considered a high voltage, which will matter for whether it's a 0 or 1 later, is 0.7 VDD. Well, for these chips, VDD is just your nominal voltage, which is 5 volts, and 0.7 of that is 3.5 volts. So what that's telling us is that at 3.5 volts, it considers it to be a high voltage. And then it's telling you that at 0.3 VDD, it's considering it a low voltage. Anything at or below 0.3 VDD, it considers a low voltage. The real key value I found in this experimentation, though, is this 3.5. Anything below 3.5, it considers low. Now the times, what these are telling you is the time high for a digital 0 is 0.5 microseconds. The time low for a digital 0 is 2.0 microseconds. The time for 1 bit includes the high time plus the low time. So the total duration of 1 bit for a low speed chip is 2.5 microseconds. However, we are using again the high speed, and that's divided by half. So it's not 2.5. For our chips, it's going to be 1.25. 1.25 is going to be the total duration of a bit. Just like the time for a digital 0 is given here, so is the time for a digital 1, high, low, and you'll see that's 1.2, 1.3. You add those together, again, you get 2.5 microseconds. Divide that by 2, 1.25 microseconds. So as we'd expect, the bit duration for a 1 or a 0 is the same. Now if we take the data from those data sheets and graph it, this is what that looks like. The top graph is a digital 0, the bottom graph is a digital 1. You'll notice the only difference between these graphs is how long the high time, the high voltage, is held. And this is straight out of that data sheet. So for a digital 0, the high time is only held for about 225 nanoseconds, and it's held for 600 nanoseconds for a digital 1. You'll notice the bit length, the total bit length, is the same for both. That's right at that 1250 nanoseconds. So one bit, whether it's a high or a low, is always 1250 nanoseconds. All that changes is how long it holds this high value. Now these graphs that I've shown are for an ideal square wave perfect electronics, which just isn't what can be fabricated. What you'll see in some of the measurements is ringing, where it's an overshoot followed by less of an undershoot, less of an overshoot, until it kind of flattens out a bit. And same thing as it drops, as it does a drop in the voltage, you'll see this kind of ringing. These chips, what I noticed is they are very tolerant of what we call overshoot, of this stuff above threshold. They're very tolerant of that, and the F-amp takes advantage of that. What you'll see the F-amp do is take and impart a large overshoot, such that it stays well above this 3.5 volt threshold, which gives it a lot of margin for this ringing down here not to drop below the threshold. So the signal I've captured here is actually a good signal. You can see based on the volts per division, this being 0, 2 volts, 4 volts, the entire signal is above the 3.5 volt threshold. Yet, and the duration here is 780 nanoseconds. This is a digital 1, which has to be 650 nanoseconds long. So again, we're well above that with margin. So 780 is greater than 650, so this would be recognized as a digital 1. But this tells me this is a good signal. But at 75 feet, I was seeing anomalous behavior in the pixels themselves. And test results mean more than any measurements do, right? But with this signal, I should have had good performance of the pixels, and I tried to figure out why. What I was noticing is that in the first pixel, I was having a behavior where it was changing properly without any artifacts or anything, but none of the subsequent pixels were. So that tells me that it is receiving good data. So either that pixel's bad or something else is going on. And that pixel's been working fine this whole experiment. I didn't think it was bad. So what I did is we are still 75 feet between the F-amp and the pixels, but I added a power injection T immediately before the pixels and injected power there. So when I did that, I got great pixel behavior at 75 feet away from the F-amp.